In this video, we're going to look at how experiments involving light led to our current understanding of the structure of the atom. These experiments also led to the development of quantum theory, which we use to describe an electron in an atom. We'll look at how electrons are distributed around the nucleus of an atom, identify the electrons which are responsible for bonding atoms together to form molecules, and look at the structure of molecules. Bunsen of Bunsen-Burner fame pointed a spectroscope at heated elements and found that different elements emit different colors and different line spectra. When a solid is heated, it emits different colors of light depending on the temperature of the solid. Planck said a minimum amount of energy, which he called the quantum, is required for atoms in a solid to start vibrating. The frequency of light emitted is determined by this formula. The temperature of the solid can be determined by the color of light emitted. So a solid heated to 3000 K is red hot, 4000 K is yellow or green hot, and 5000 K is blue hot. So the hotter the solid, the shorter the wavelength emitted. When light of a certain wavelength hits the metal, an electron is ejected from the surface of the metal. This was a strange observation. How does a wave of light interact with a particle? Einstein theorized that light behaves like a wave and a particle, which he called a photon. Here are a few applications of the photoelectric effect in which a photon produces an electron. I'm dating myself, I know, but the Star Trek TV show applied the dual nature of light. In Rutherford's experiment, he and his students shot alpha particles at a gold foil. Most passed directly through the foil. A few were deflected, and even fewer were deflected right back at the source. Rutherford figured the alpha particles that were deflected bounced off the nucleus. He concluded most of the mass of the atom is contained in the nucleus, most of the volume is in the electron cloud. No one was able to calculate or predict the emission lines in the hydrogen emission spectrum until the physicist Niels Bohr came up with a model in which he assumed that the energy of an electron in the hydrogen atom is quantized. And de Broglie thought that if light, which is a wave, can behave like a particle, maybe matter, which is a particle, can behave like a wave. Electrons, which are particles, were shown to behave like waves when electrons were observed to diffract through a crystal. Diffraction is a property of a wave. So both light and matter were shown to have a dual nature, that is, wave and particle properties. De Broglie's equation relates the wave nature of matter to the particle nature. A microscope uses the wave property of its illumination source to view very small objects. A microscope's resolution is the smallest object that can be observed. So stop the video and answer this question for a light microscope. And the answer is 200 nanometers is 0.2 microns. So if I remember my biology, that allows us to use a light microscope to see inside a cell. An electron microscope can view much smaller objects than a light microscope. So stop the video and calculate the wavelength of an electron in an electron microscope and compare this wavelength to the wavelength of a baseball traveling 60 miles an hour. And the answers are... So this is the wavelength of an electron in an electron microscope. And using de Broglie's equation, this is the velocity the electron travels. Magnets are used to achieve that velocity. The wavelength of a baseball traveling 60 miles an hour is much, much smaller than the wavelength of an electron. So very small particles traveling very, very fast show wave properties, not so much for large objects traveling slow. The ideas of quantization and matter having a dual nature led to the development of quantum theory. Classical physics treats a particle as a particle, but quantum theory treats a particle as a wave. In classical physics, Newton's laws are applied to determine the position and energy of large objects moving slowly. In quantum theory, we can look at the probability of a small object moving very fast being in a certain region of space with quantized energies. So let's review. Stop the video and answer these questions. And the answers are, if you are in your room, the probability is 100%. Electron cloud refers to the region of space where there's a high probability of finding an electron. Stop the video again and answer questions 1 and 2. And the answers are, we'll answer questions 3 through 6 in the next few slides. Here are a few applications of quantum theory maybe you'll be working in one of these areas in your future. An atomic orbital describes 4 quantum numbers, which tells us all the information we need to know about an electron. Stop the video and review the information about quantum numbers. Let's relate the quantum numbers to the atomic orbital designations. In a 3p atomic orbital, the 3 refers to the principal quantum number. For a p orbital, the angular momentum quantum number equals 1. The magnetic quantum number depends on the angular momentum quantum number. So if L equals 1, m sub L can have 3 values, 0, 1, and minus 1. This tells us there's 3 different orientations in space for the p atomic orbitals. You've heard of them before, the px, py, and pz atomic orbitals. The spin quantum number tells us the orientation of electron spin. There are 2 possible values, plus 1/2 and minus 1/2. So stop the video and determine the quantum numbers for an electron in a 4s atomic orbital. And the answers are: atomic orbitals tells us about the energy of an electron, which tells us about color. Remember how different colors of light are emitted in emission line spectra. The energy of an electron also tells us about the reactivity of a substance. The higher the energy, the more reactive that substance is. The shape and orientation of an atomic orbital tells us the region in space where there's a high probability of finding an electron. Later, we'll see how orbitals tells us about how atoms bond together to form molecules, as well as the shape of molecules. Quantum theory tells us how electrons are distributed around the nucleus of an atom. We often want to know the lowest energy electron configuration, which is called the ground state. Stop the video and review these 4 rules for determining the ground state electron configuration of an atom. The ground state configuration of hydrogen is 1s1. Helium has 2 electrons, so the second electron goes in the 1s atomic orbital with opposite spin. Lithium has 3 electrons, so the third electron goes in the next highest energy atomic orbital, which is the 2s orbital. Let's apply Hund's rule in the next example. Stop the video and answer these questions. And the answers are: carbon is represented in each diagram, and B is the ground state electron configuration. According to Hund's rule, the p atomic orbitals fill 1 orbital at a time with the same spin before pairing up. Note in diagram C, the electrons in the p atomic orbitals have opposite spin, which makes it an excited state. The valence electrons are very important electrons because those electrons are involved in bonding. The valence electrons are farthest away from the nucleus and occupy a partially filled shell. So stop the video and answer these questions. And the answers are: the n quantum number tells us about the shell. Note that the L shell is partially filled, so those 5 electrons are the valence electrons. A look at the periodic table also tells us about the number of valence electrons. Nitrogen is a group 5 element, so there's 5 valence electrons.